Hi, my name is Molly Wakeling. I write for Astronomy Magazine, the Observing Basics column, and I've been doing astrophotography for almost exactly the last 10 years as of, I think, a week or two ago. I got into visual observing as well as do a lot of astrophotography. And so today I'm going to talk about choosing eyepieces, filters, and accessories in order to get the most out of your visual observing. So, one of the first things to think about is what kinds of things do you want to see? And you might be like me and want to see everything, or you might be interested in some particular types of objects which can help you decide what eyepiece to buy first, at least. So do you want to look at wide sweeping star fields, stellar nurseries, supernova remnants, itty bitty planetary nebula or galaxies? Planets, star clusters, double stars, lots of different things to see that have different considerations when choosing your eyepieces. So first I'm going to go through a set of terms because there's a lot of terminology involved with eyepieces to understand what all of those mean so you can help inform your decision for buying an eyepiece. And then I'm going to talk about filters and accessories. All right, so first thing is size. There are two main modern sizes, 1.25 inches and 2 inches. And this is the size of the barrel that slides into the focusers, is what that means. There's also a common older size, 0.965 inches, that you may come across sometimes, although you'll see those more like at yard sales or astronomy clubs than you'll see online these days. Another consideration with that is, do you need an adapter, and does your telescope fit a 2-inch eyepiece? So if you have a 2-inch focuser, you might need to get an adapter for 1.25 inches, or if you have an 1.25 inch focuser, then you won't be able to use a 2-inch. You also have to consider weight. 2-inch eyepieces tend to be larger and heavier, and you have to think about whether your telescope can support that extra weight or not. So magnification, this is an often misunderstood number, and it's often thought that you want as much magnification as possible, but that's not entirely true. So magnification is basically the amount larger that the object appears in the telescope than it does to the naked eye. And the way to calculate that is actually pretty simple. You just divide the telescope focal length by the eyepiece focal length, like I have a little pictogram on the side there. For example, if your telescope is 1,000 millimeters focal length and your eyepiece says 10 millimeters focal length on the side, that means that eyepiece with that telescope will give you 100x magnification. More magnification is not always better. If you're looking at a planet, then you might want to get as much magnification on there as your telescope and this atmospheric conditions will support. But otherwise, you may want to back off quite a lot, especially if you're looking at a large star field or a large nebula. For a point of reference, 150 to 300x is considered to be high power. You often hear people say low power versus high power. This basically just means low magnification versus high magnification. And as a note, lower power means a brighter image because at higher power, at higher magnification, you're spreading out the same amount of light over a larger, over the whole field of view of the eyepiece as opposed to concentrating it more into a smaller area. So with a higher magnification eyepiece, the image will look dimmer. So, what is focal length? That is the distance from the lens to where the light focuses. So the picture on the bottom here, the focal plane is actually before the eyepiece, and then the light gets collimated and then refocused onto your eye. You're basically magnifying the image of the focal plane. That's where the magnification comes from. It's measured in millimeters, or at least everywhere that I've seen it. Smaller focal length means more magnification, and larger focal length means less magnification, kind of opposite of what you might think. But over here on the side are two pictures to kind of show what that difference in magnification looks like from the difference in focal length. So on the top is a 10 millimeter view, which looks at just the core of Andromeda here on my example 1000 millimeter telescope. Or with a 40 millimeter eyepiece, you get a much broader field of view, can see the entire galaxy. Now, of course, it won't look exactly like this through the eyepiece. Our eyes are not as sensitive as the camera is here. With the camera, we can take very long exposures. So when you look through the telescope, this will look a lot dimmer and won't have the color, but it's still an awesome sight to look at a galaxy that's millions of light years away. So for example, here, that 10 millimeter view is 100x and that 40 millimeter view is 25x. Apparent field of view. So usually the second number commonly associated with a particular eyepiece, aside from its focal length, is its apparent field of view. And this is a number that's in degrees, like 45 degrees or 60 degrees or 100 degrees. And this is the width of the sky presented to your eye in degrees independent of your telescope. So a larger apparent field of view means a larger field of view if you're using the same for the same focal length eyepiece, but also for the same magnification. So even though the field of view is larger for a 100-degree AFOV eyepiece, it's actually the same amount of magnification. It's just broadening the amount of that light column that's coming into the telescope so you can see more of the image. Now, these larger AFOV eyepieces also tend to be more expensive and also tend to be a lot heavier. So you have to take that into consideration when thinking about what size AFOV eyepiece you want to invest in. Eye relief is the number you'll hear thrown around a lot as well, and you might see it in the text of the description of the eyepiece online. It's the distance from the last lens surface, so basically the top of the eyepiece farthest away from the telescope, to where your eye needs to be in order to see the entire field of view without getting cut off on the edges. This is usually also measured in millimeters. Larger eye relief means that you can be farther away from the eyepiece and still be able to see the whole field of view. This is great for people who need to observe with glasses, and it's also great for kids. It's hard for kids to kind of get their eyes up really close to the eyepiece without hitting it with their eyeball. But these eyepieces are also bigger and heavier. Now, if you're a glasses wearer, if you only wear glasses for near or farsightedness, I recommend not wearing them when you're observing because you can just refocus the telescope a little bit to fit your vision. This way you can be closer to the eyepiece and also not smudge your glasses. But if you wear glasses for astigmatism, like I do, then you may want to keep those glasses on so that the stars don't have those odd little spikes. My astigmatism is minimal enough that I tend to observe without my glasses, at least through a telescope. When I look up at the sky, I'll put them back on. Exit pupil. This is the width of the image coming out of the eyepiece. Generally speaking, higher power, higher magnification, so shorter focal length eyepieces have a smaller exit pupil. For example, the 7.5 millimeter Plossl up there on the top. A smaller apparent field of view also tends to make for a smaller exit pupil. And the exit pupil can be too large if you're using a reflector. You generally want to keep that below 7 millimeters, or else you will see the kind of a darkened area in the middle of the secondary of the telescope as sort of a black splotch. So an example here comparing how AFOV comes into this, if you have a Plossl like the 7.5 millimeter one on the top, that's a 52-degree apparent field of view. It's cheaper, but it's got a tiny little hole that you have to look through. Whereas this more expensive Televue Nagler eyepiece on the bottom has, it's about the same focal length, has a larger apparent field of view, and also has a larger exit pupil. So it's a lot easier to look through than the tiny Plossl on the top, but is much more expensive. So when you're thinking about eyepieces, there are some other things to consider as well. You want to maximize the true field of view, but have that at a high enough magnification to be able to get the view that you want. So if you're looking at a large, let's say you're looking at the Veil Nebula, which is a large supernova remnant, you want to be able to see the whole thing in the eyepiece, then you'll want to use a longer focal length eyepiece with less magnification. But if you're looking at a planet, then you're going to want to use as much magnification as the telescope and the atmosphere can support. Double stars and planetary nebulae are similar for small planetary nebulae. There are also large ones too. And a way to kind of a quick rule of thumb on how your telescope aperture limits how much magnification you can use is about 60x per inch. So if you have a 10-inch telescope, it can support as high as 600x if the atmosphere is behaving nicely that night. Too high a power, you'll see mount shakiness, you might see eye floaters. And if you have a telescope that's not tracking, then that target will drift through the eyepiece so quickly that you won't be able to enjoy it for very long. A good reference here is about 125 to 150x is great for globular clusters, where you want that magnification to be able to separate the individual stars, but also need some more field of view to be able to fit the whole thing into the eyepiece. And so you may end up with a variety of eyepieces for different observing goals, different things you want to image that night. A lot of people end up with at least 3 or 4, if not 20. It depends on how deep you want to go. I think I have about 6 I take out with me with my 12-inch telescope. Some other considerations are cost. Plossls are cheap, but they have small apparent fields of view. small eye relief, and small exit pupils. Something that's really fancy, like a Teleview enagler, is expensive, but they have large apparent fields of view, large eye relief, large exit pupils, depending on the design, and also are very crisp and sharp and really a joy to look through. Um, you also have to consider, is it so heavy that it makes your Dobsonian or the diagonal in your Schmidt-Cassegrain telescope sag? We need to adjust the balance of your Dobsonian in order to use it if it's really heavy. And do you want to carry around a bunch of large eyepieces, or would you rather carry around smaller ones that are decent? I actually really like my 23 millimeter Celestron Luminos. It's one of the main ones I use with my 12-inch, and it kind of has a nice balance between magnification, field of view, and exit pupil, and how large that aperture is there. All right, so that's it for eyepieces. Let's talk about filters. So what are they for? There's a variety of different filters for lots of different observing goals. So there are ones that reduce light pollution, which is helpful when you're observing from somewhere like Bortle 4 or higher, somewhere that's closer to the city. It won't make up for dark skies, but it can help increase the contrast a little bit. There are specific nebula boosting filters that can help increase contrast for emission nebulae like planetary nebula, stellar nurseries, and supernova remnants. There are the color filters, so you can see different aspects of planets. There are some that can reduce purple fringing that comes from certain types of refractors. And when you're looking at a full moon, it can sometimes just really blind you. So having a neutral density filter to reduce the brightness of the moon can also be really nice, especially when you're trying to still see in the dark, particularly at like a public stargazing outreach event. So an example of what a nebula filter is, it can boost the contrast in emission in planetaries, nebula, and supernova remnants. For example, the Veil Nebula, the Lagoon Nebula, the Eskimo Nebula, etc. And it doesn't increase the brightness, but it increases the contrast. So it's easier to see against the background. And you can kind of see an example of that in the picture here, which is, maybe a little bit exaggerated, but not too far from the truth. Some of those are called ultra high contrast or nebula boost or O3 or H beta filters. And some common manufacturers that make those are Lumicon, Astronomic, Orion, others as well. I think I have an Optolong somewhere in my kit. Planet filters, you use these color filters to increase contrast of specific kinds of details for specific planets. So for instance, you can use different colors to look at different Mars geographical features. It's clouds or it's polar caps. You can sometimes discern clouds of Venus with particular color filters, and also make Jupiter's Great Red Spot stand out more, or make its other cloud bands stand out more. There's some great articles that go into a lot more detail on which filters to use for what online, but that's an example of the kind of filters that are out there. All right, other accessories. So I love Telrads. A lot of visual observers love Telrads. It's sort of a large device that you can even attach it to the top of your telescope with Velcro if you don't want to drill holes into it. But it is a no magnification finder scope. So it just has a red lit bullseye, and you look up through it and you can see where you're moving the telescope and see what star it's sitting on, instead of trying to figure out which way you're actually moving in your like inverted finder scope, or trying to figure out if that bright star on the finder scope is actually the bright star that you're pointing at. So these are really easy to use and are great in conjunction with a finder scope. But I actually just use that on its own with my 12-inch. They run about $50. Some apps that are really useful. I love Sky Safari. There's a free version called Sky Portal. Sky Safari just has a larger catalog of objects, and also you can connect it to certain kinds of telescopes to control them. It's a planetarium app available for Android and for iOS, and it has descriptions and pictures, and shows you where in the sky to find things. And I've used it quite extensively, both for astrophotography and visual observing. If you prefer to do all of that planning in advance on your desktop computer with a bigger screen, Stellarium is a great app for that. It's available on Linux, Mac OS, Windows, all kinds of platforms. It is also available for mobile, but I find it kind of hard to use on mobile. Also a red screen app. So I use Twilight on Android. There's also Night Vision Light on iOS. And this will make the screen a true red, as opposed to just kind of the yellow that the night light feature will make it. That way, A, you can look at it at night and not lose very much of your night vision, and B, you're not bothering your neighbors if you're looking at your phone at night, looking through Sky Safari, trying to find targets, or things like that. Finally, I also some other accessories that you can get are an observing chair. This way you can sit at your telescope and enjoy that view for longer instead of stopping when your back hurts. Um, Getting an observer's notebook. So it's really good to keep a logbook both for just both to track your journey of how you grow as an observer, but also to make you a better observer. By taking notes of the things that you're looking at, you start to pay attention to more details and more features. And also, the Astronomical League observing programs require that you take notes. So this is a great place to do that. A star atlas. This is I find them a lot easier to use than the phone app because the star charts are much more clear than trying to see them on the phone. Plus, then you don't have a phone screen to contend with, and they're really helpful for finding objects all over the sky. And some red lights to look at that star atlas with and look at your notebook with, and a dim red light, because a bright red light will still ruin your night vision. If you have a dim red light, then you can maintain your night vision, not bother your neighbors, but still be able to look at your star atlas in your observer's notebook. And lastly, join an astronomy club. They're full of people who love to share views through their telescopes, love to give advice. If you don't have a telescope yet, you can go look through either the club's telescopes, or people who are in the club look through their telescopes. People are generally pretty happy to share the views through their scopes and teach you what they know. It's also a great place to socialize and observe together, which can make it much more fun. You'll learn lots of new objects, lots of new techniques, and also just make new friends. And that's all I got for eyepieces, filters, and accessories. Clear skies.